say this is the last lecture. We don't have much left. A couple of different formulas, one dealing with kinetic molecular theory, or root mean square, velocity, and diffusion. Very simple. Couple of things that you need to pay attention to. I'll point out to you as we go. We've already looked at energy or kinetic energy, and we can calculate it with the formula here. And all we need to know is the mass of the particle and the velocity here, right? So u squared is the velocity squared, and m is the mass, and so the product of the two is equal to the energy in joules. Anyway, if kinetic molecular theory states that 1 mole of hydrogen and 1 mole of oxygen have the same kinetic energy, and obviously they differ in molecular weight, then what must be true about that is that they are traveling simply at different speeds. And so that makes perfect sense that a smaller particle, in order to have the same kinetic energy as a larger particle, will move much faster, right? So it's simply the product of these two has to be the same for hydrogen and oxygen and argon and any of these. And since they all have different masses, that means they must travel at different speeds. And that's what kinetic molecular theory is all about, right? So there are 5 postulates. I'll go through them pretty quickly. What's really important is that there are no intermolecular forces here, right? So the forces of attraction, repulsion are negligible or super weak, which means that if you don't have molecular forces holding two particles that are traveling in the gas phase together, then there's nothing to stop them here, right? So the size again of these is negligible. Whether we have hydrogen or oxygen or argon, they all occupy the same space if they are at the same volume and temperature. And so what that means is they're going to move in random straight lines, since they don't hang on to each other. They don't interact much with each other. They're just going to go in a straight line. Some go this way, some go this way. They're going all over the place unless they hit each other, and then that collision, when they hit each other, is said to be elastic. And what that means is, where to go here, elastic, and that just simply means that when they don't lose any speed, they just bounce into each other and continue traveling at a different path, right? So two particles that hit each other that were traveling in this direction, then one is going to get deflected and go this way, the other one is going to get deflected and go this way, but the speed is still going to be the same. Okay, and so then the average kinetic energy of a molecule is proportional to its absolute temperature. Again, it's not dependent on volume or temperature. It's really just, well, no, the temperature, the absolute temperature and kinetic energy, right? Okay, so if we look at a graph of velocities, not energies here, so these are the speeds of different particles and the relative number of molecules and its distribution here, right? So this is where volume and temperature are constant. And this is for 1 mole, let's say, of each of these substances, helium, hydrogen, and so on and so forth. No more bonus points here. But what you see here is that the maximum here is the average kinetic speed of a particular type of molecule here. So, okay, and so oxygen, that's just the average molecular speed, velocity here, right? And so some particles move slower and some particles move larger, right? So that's indicated here. And so the very small ones move much faster. In fact, there are some that are moving very fast here at very high speeds. And so the distribution is just much wider, and that makes sense. So again, this is just for 1 mole of each of these substances, and so the average kinetic energy of 1 mole of these is equal. That of hydrogen is equal to that of oxygen, but not the speed, right? So the hydrogen, the smaller molecule, will travel much faster than the larger molecule, right? And so the smaller they get, the wider the distribution. This is really enough said about this slide here. It's pretty straightforward and intuitive here. Now we're looking at 1 mole of nitrogen simply at different temperatures, and it also makes sense that as you increase the temperature that that you increase the average molecular speed here, right? So at higher temperatures, at 2000 K, you have a higher molecular speed than you would at 0 degrees Celsius or 273 K, right? So that's also very intuitive. And you may want to think about how that would affect density, which is mass over volume here, right? So I'll let you do this on your own. Okay, so let's go right down to it, right? Okay, so what we're looking at is this is a special kind of average here, right? Because it takes into consideration all of the molecules and all of the speeds here. And so we call that the root mean square molecular speed here, RMS. And there's a formula for it. Here, U equals root mean squares. It's 3 times R, which R is a constant. And then the constant has units that are in kilograms, and I'll give you that constant in a minute on the next page. Kilograms times meter squared per second squared per degree Kelvin per mole. Okay, so those are the units of R, right? So then temperature is in Kelvin, and here this is the molecular weight, and so the molecular weight has to be in kilograms. So this is what you want to watch out for: kilograms per mole. So if you have hydrogen, which H2, right, has a molecular weight of 2 grams per mole, you have to convert that to kilograms per mole. And all you do, you'd simply say 2 times 10 to the minus 3 kilograms per mole. So you must remember to convert molecular weight to kilograms per mole when you work with this formula, and by gosh, it's going to be on the exam. And but you should have access to these units, and that serves as a reminder. So you just simply plug that in for any particle. Here's R. Again, it's 8.312. And so all we have to do here is to calculate the root mean squared of helium in a vessel at 21 degrees Celsius. Here we need to convert Celsius to Kelvin, and that would be 293. All right, you just have 273 plus 21 is going to be 294 K. So I'm just going to plug this stuff in here. So we've got the square root 3 times 8.314 kilograms meters squared per second squared times K times mole times that 294 K. So K already cancels, and then the molecular weight. A helium is 4.003 grams. So what we plug in here is 4.003 times 10 to the negative 3 kilograms. So kilograms per mole, mole cancels, and then you take the square root of meters squared per second squared, and you get meters per second. And in this case, we have 1,350 meters per second. That's the speed of helium at 21 degrees, right? So here it is just worked out nicely, 294. Now if we take that same gas and we increase the temperature to 37, all that's changing is T, right? So all we're going to change is, and I'm going to bring it up, the only difference is here, this went up from 294 to 310. And we do see an uptick in molecular speed from 1350 to 1390, right? So that makes perfect sense. Now if we keep these conditions but we replace the molecule here, hydrogen, it has a much smaller molecular weight. So we expect that to go up, right? And that's exactly what happens, right? So the only thing that changes this time is the molecular weight. Instead of 4.0 times 10 to the minus 3 kilograms for helium, we are using 2.0. I got to remember the thing that hydrogen is diatomic, so it's not 1 gram per mole. So all of those gases, N2O2 and chlorine, if I ask you to calculate that as well. And so see how drastically the speed goes up, right? So the speed went from from 1390 to 1966, going between on the same conditions, same temperature, and so this is kind of irrelevant because ATM, it also has to be the same. Well, right. Okay, so that's that. You should not have any trouble with that. It's pretty simple. And the last thing that's left is diffusion, right? So diffusion is just the process at which gases spread, right? So it makes sense that smaller molecules can spread faster. And so we use this here. If you want the molecular weight of these substances is obviously connected to its rate. So if we compare the rate of A, let's say it's helium versus hydrogen, and so the rate of A over the rate of B equals the square root of molecular weight. And so you flip-flop these here, right? You see that? Anyway, let's just do an equation with that. So if I was to look at the rate of O2 versus the rate of H2, I would use this equation. And so if so that rate of H2 versus the rate of O2 is then just simply 32 divided by 4, which is, and then the square root of it is 16, and then the square root of 16 is 4. So it's 4 times faster, right? So that means this is 4 over 1, right? Or 8 over 2. So the diffusion of hydrogen is 4 times faster than the diffusion of oxygen. So this is not very difficult to do. If you accidentally, what can happen is that you switch these two, and then your math doesn't come out very well. So what you want to do is you want to put the larger molecular weight on top. Okay. All right. So here's that, and then I could also ask you for an unknown gas effuses at a rate of 0.46 times faster than the rate of nitrogen gas. All right, so I know this here, this ratio is, but then solve for x here, right? So I take the square root of that, not the square root, I square that. That's a molecular weight of 131 grams per mole. This is the end. I can't say it's been a pleasure because I never met any of you, but either way, have a good one. Good luck on the final.